Hey everybody, Trey here. Welcome back to another video. Today we're going to dive into one of the more widespread tornado outbreaks of the 2024 severe weather season, and that is the May 25th and 26th outbreak that stretched from the southern plains to the eastern seaboard. From a meteorological standpoint, this outbreak featured numerous highlights, including the long-track tornadic supercell that tore a path through North Texas, producing EF3 damage near Valley View, the supercell that produced separate EF3 tornadoes near Claremore, Oklahoma, and Decatur, Arkansas, the latter of which was nearly 2 miles wide at times, and many others. In this video, we're going to break down the complex meteorology behind this setup, including why much of the risk area on the 25th underperformed, what fueled the long-track intense tornadic supercells after dark on the 25th, and how the environment quickly trended up for a second round of tornadic supercells on the 26th. So without further ado, let's go ahead and get started. We'll begin with May 25th. The first indication from the SPC that a potentially significant severe weather event was on tap for May 25th came with the Day 5 outlook on May 21st, in which a 15% area was delineated across Arkansas, southeast Oklahoma, and North Texas. The 15% risk area was expanded in the following day's Day 4 outlook before a Level 3 out of 5 enhanced risk and associated 30% hatched area for significant severe weather were added in the Day 3 outlook on May 23rd. The forecasted environment quickly ramped up over the next several model runs, and by the midday outlook on May 24th, the SPC had upgraded to a Level 4 out of 5 moderate risk across Kansas and Oklahoma, with a 15% hatched area for significant tornadoes, a 45% hatched area for significant damaging winds, and a 30% hatched area for large to very large hail. In this outlook, forecaster Ryan Jewell noted that only reduced confidence in storm coverage was precluding an upgrade to high risk. However, the SPC opted not to upgrade to high risk in subsequent outlooks, and the moderate risk remained through the day on the 25th, with only some shifts in the outlook area during the afternoon and evening. Alright, let's dive into the meteorology behind this event on the 25th. As always, we'll begin at 500 millibars at 12Z, 7 a.m. Central on May 25th. Our main synoptic scale feature of interest was this shortwave trough and associated jet streak situated across the southwestern U.S. This feature translated east during the day, with the strongest flow overspreading the southern plains throughout the afternoon and evening. The low amplitude nature of the shortwave and more westerly flow aloft helped keep large-scale forcing for ascent subdued, which kept storm development more isolated to widely scattered. Up at 300 millibars, we see much of the same pattern with our trough and 100-plus knot jet streak situated over Arizona. Given the jet streak's lack of curvature and zonal nature of the flow, upper-level defluence was fairly minimal throughout the day, additional evidence that synoptic scale forcing for ascent was on the weaker side with this event. Several ripples were embedded within the flow at 700 millibars, indicative of smaller-scale shortwaves. Additional shortwave troughing developed from eastern Colorado southward into the Texas Panhandle by mid-afternoon, timed well with daytime heating to provide some subtle assistance to storm initiation across the central and southern plains. Through early evening, a convectively enhanced shortwave became apparent from Kansas into northern Oklahoma, quickly moving off to the northeast. Down at the surface, the pattern was fairly quiescent to start the day, with an area of high pressure situated over the Midwest and a lack of significant surface low development anywhere in the plains, leading to somewhat weak, chaotic surface winds. However, this would change quickly. As the westerly flow within the intense mid- and upper-level jet streak began to traverse the higher terrain of the Rockies, robust surface cyclogenesis occurred across eastern Colorado, helping to strengthen surface winds and better define the overall surface pattern. The low would meander east into Kansas during the late afternoon and evening. Switching to our raw surface data, you can clearly see the lack of a defined surface pattern at 12Z. Notice that winds across much of North Texas, Oklahoma, and southern Kansas were out of the east or northeast, which is an unfavorable trajectory for pumping robust Gulf moisture into the area of interest. With the richest moisture along and south of the Red River in Texas, we need surface low development to help those winds shift to more southerly and effectively transport that moisture northward into the moderate risk area, and how quickly that occurred would be key in delineating the northern extent of the significant severe weather risk. A stationary front was situated from southern Missouri into northern Arkansas, southeast Oklahoma, and north Texas, as evidenced by the distinct temperature gradient but quiescent winds on both sides of the boundary. Note the temperatures in the upper 50s and low 60s north of the front, with temperatures in the upper 60s and low 70s to its south. Otherwise, there was little in the way of any notable boundaries thanks to the lack of a surface low, aside from the beginnings of a dry line in southwest Texas. As we head into early afternoon, the surface low began to take shape in eastern Colorado. surface winds quickly turned to a more southerly direction, initiating the northward advance of the more robust moisture into the moderate risk area. As a result, the stationary front turned into a warm front, demarcating the leading edge of the advancing moisture. The dry line had developed northward, stretching from West Texas into southwest Kansas. 70s dew points had been advected into a corridor from southwest to northeast Oklahoma by 18Z, priming the environment for significant severe weather. Storms would initially develop in northwest Texas, where temperatures had soared into the low 90s. However, rich moisture struggled to advect into areas to the north ahead of the dry line. Dew points remained in the 50s and low 60s across northwest Oklahoma and southern Kansas, even into the late afternoon time frame, yielding high-temperature dew point spreads unfavorable for tornadic supercells. This meant that storms initiating along the dry line here would be outflow dominant until they reached better moisture to the east. This was similar to what plagued the daytime convection during the May 6th high risk in Oklahoma, in which two distinct dry lines developed, as I discussed in my breakdown video on that event. Storms developed along the westernmost dry line, which featured relatively drier air ahead of it, leading to convection struggling with outflow dominance and quicker upscale growth. Back to May 25th, the area to the south across Oklahoma and Texas did not have this issue. Instead, moisture had continued to climb, with dew points pushing 75 degrees across central and southern Oklahoma and 80 degrees across north Texas. This continued into the evening given strong warm advection induced by the deepening of the eastern Colorado surface low, and a large swath of eastern Oklahoma, Arkansas, and Texas was under the influence of extremely rich low-level moisture, further improving the environment. Let's now take a look at some observed soundings from across the region to see what the environment looked like to start the day. We'll start out at Norman, Oklahoma at 12Z, and you can see a couple important features right away. First, a stout capping inversion was in place beneath a healthy elevated mix layer, that layer of warm, dry, well-mixed air that emanates off the higher terrain out west and gets transported atop the moist layer over the plains. Low-level moisture was limited at this point given that Norman was located north of the stationary front. Some elevated instability was already in place, expected to increase with strong surface heating during the day, and continued warm moist advection as the eastern Colorado surface low developed and intensified. The wind profile at Norman was already quite elongated, indicating strong deep layer shear was already in place. As expected, low-level shear was quite weak thanks to the lack of a robust low-level cyclone and associated low-level jet at this time. Down at Fort Worth, Texas at 12Z, ample instability was already in place, with mixed layer CAPE approaching 2,000 joules per kilogram atop a capping inversion. Low-level moisture was a bit shallower than at Norman, but still adequate to support severe weather. Once again, the wind profile featured strong deep layer shear but minimal low-level shear. With low-level cyclogenesis expected to occur through the morning and afternoon, low-level shear was forecast to increase. The question was how rapidly this would happen, as convective evolution across the moderate risk area was tied to the evolution of the wind profiles. We'll come back to this in a second. Storms first initiated near the Guthrie area in northwest Texas just after 1 p.m., where convective temperatures were easily breached between 18 and 19Z. Given the strong deep layer shear in place, they quickly morphed into supercells. However, notice the amount of storm splitting that occurs right off the bat. Several left splits, complete with robust outflow, surged into southwest and central Oklahoma over the next several hours, effectively ending the significant tornado threat there. This was a notable source of uncertainty leading into the event. In their morning outlook, the SPC noted that the development of only isolated/few storms in Texas may greatly increase the threat in Oklahoma. By contrast, dense coverage of afternoon convection over west central and northwest Texas may affect potential farther north, whether directly through left split interactions or indirectly via outflow-related theta E deficits advected northward. In reality, while we didn't see widespread convection develop in northwest Texas, we saw both efficient left split production and cold outflow production. Plus, storms initiated quite early in the event across northwest Texas, giving these left splits ample time to negatively impact the environment across central Oklahoma before storms matured farther north along the dry line. This was all due to the environment. The cap, which wasn't all that strong to begin with in North Texas, was easily eroded via strong surface heating and low-level warm advection, as evidenced in this 21Z observed sounding at Fort Worth. In addition, as surface temperatures warmed across this area, temperature dew point spreads inched up to near or just above that rough 20-degree threshold for tornadic activity. This promoted significant outflow production, particularly with the left splits as they tracked north into Oklahoma. Now, why did we see so many left splits? This can be traced back to the wind profile. The hodograph had remained relatively straight with only modest low-level hodograph curvature due to 1 kilometer winds increasing from 10 knots to near 25 knots by 21Z. Straight hodographs like this typically favor splitting storms. In environments with straight hodographs, distinct areas of cyclonic and anticyclonic vertical vorticity develop on the southern and northern flanks of nascent storms, respectively. These then split into separate right and left movers, with the right movers having the best chance of producing tornadoes and the left movers favoring hail. Often, the left movers will fizzle out, but that was not the case in this event. The left movers and their associated outflow continued to remain intense as they tracked into Oklahoma, washing out what was a favorable environment for tornadic supercells. As this occurred, the main right mover within the northwest Texas convection intensified, producing a tornado near the town of Windthorst just after 5 p.m. The wind profile featured just enough low-level shear to support tornadogenesis, along with some likely assistance from auxiliary storms on its western flank. This is Cameron Nixon's nudger theory in action. Meanwhile, supercells developed along the dry line farther north, first in the Oklahoma Panhandle, followed by the northeast Texas Panhandle. As we discussed earlier, these were developing in an area of much more meager low-level moisture, with temperature dew point spreads approaching 30 degrees Fahrenheit. Still, the southernmost of these supercells produced a brief tornado near Mutual, Oklahoma. The northernmost of these dryline storms tracked into southern Kansas. Just before 7 p.m., left splits from the Mutual, Oklahoma storms merged with the southern Kansas supercell, leading to intensification and setting off a unique chain of events that included potentially non-mesocyclonic significant tornadogenesis near the town of Anthony. To dive into this, I'm going to turn it over to my friend and fellow storm chaser Mikey Williams, who's in the process of writing an in-depth research paper on the Anthony, Kansas tornadic supercell and its unique behavior.
Thanks, Trey. Hey everybody, it's Mikey Williams here. Mesoscale Mikey is what some of you may know me as. So I wanted to talk a little bit more in depth about the storm evolution that occurred in southern Kansas on May 25th of last year. So that big tornadic supercell that tracked near Hazleton and Anthony underwent a destructive merger with a left split supercell. But it was not quite supercellular by the time it got to it. It's more kind of a surging blob, if you will, kind of like an MCS with a large outflow boundary. Had a lot of rain with it, so it kind of just knocked the storm off the face of the planet, if you will. So this supercell, although it was cut short, its lifespan was cut short, unlike the Valley View and Claremore, Oklahoma and Arkansas supercells. It was tornadic and did make it to tornadic status and SIG severe status after it tapped into the higher intensity environment after around 7 p.m. So, from my vantage point, some things I could notice with the storm to indicate that it was strengthening were an uptick in cloud-to-ground positive lightning bolts coming off of the anvil, as well as the appearance and enlargement of inflow bands into the storm coming in from the southeast, implying that it was sucking in more inflow, and as well as just vorticity as well through that. You can also see the base of the storm off here in the distance. So you notice how there's no wall cloud really, just a few little fingers that you may barely see right here. As we go forward, a few minutes later, the storm would rapidly develop an intense wall cloud. And this wall cloud, you could actually see it move south a little bit as the RFD, very intense RFD winds were pushing that kind of south-southeast or east-southeast actually. And you could also see dust start to wrap around the backside of it from this angle. Some time goes on, and after that, it produces a few brief it would appear to be at least a couple brief tornadoes around the 7:18 to 7:23 p.m. time frame, and these would have been just on the western fringes of Harper County, between kind of in between Hazleton and Anthony. So although there were these brief weak tornadoes, the main event from the storm was the EF2 tornado that unfortunately hit that farmstead west of Anthony, Kansas. About, I believe, 6 to 10 miles west of Anthony there. So we'll dive into what caused this tornado, as it's not quite the exact tornadogenesis process that you're likely used to, and I think it's being really confused with some of the other possible tornadoes from this storm, and I think that deserves to be recognized and discover why exactly this happened the way it did. So we take a look here. I apologize for this hiding the time of the radar grabs down here. However, this is just a graphic put together showing the velocity of that EF2 tornado, as you can see back here, it started down here east of Ruella Township and moved to the northwest, which is very, very unusual for a supercell for a supercell to produce a tornado when that supercell is moving due east. So that immediately caught my eye, and that's how I found out about this. So anyway, back to this. We see an area of broad rotation here. However, because this left split boundary, this is what this all is moving northward so darn fast, it makes this couplet here hard to discern at first, which is why I did not even see this in the field. Most people didn't. Right. So this is a lot like you'd see with, say, a QLCS tornado or a hurricane mesovortex, for example. However, as we move forward, this to around 7:30ish, this becomes a little bit more pronounced on radar, and it's now on the ground as an EF2 tornado. Then it peaks kind of around, say, 3:21ish, I believe. Sorry, this is blocking it. So the circulation peaks here. Notice how the location of EF2 damage is actually a few miles to the north here along Highway 2. So this implies that this tornado may have even been stronger than it was rated, because it actually, you'll see the tornado, the circulation gets a lot smaller and appears to weaken as well as it approaches this location of EF2 damage. So we move on to after 7:30, and we see the circulation move farther to the north, and it also appears to take a bank to the left, and we'll explain why that is exactly here in a second. And also note how another similar circulation, only smaller, appears to develop just to the east of that, southeast of that, which I think is really interesting, and we'll also touch on why that's the case here in a second. As you can see, the circulation rapidly constricts, but also appears to diminish a little bit, at least a little bit in strength there, and then it encounters the forward flank and rear flank downdraft surge of the parent supercell, where its inflow would be cut off, and therefore it dies just after impacting that homestead there on Highway 2. So let's put it in motion, exactly show what happened with this storm. So you can see this supercell here, pretty beefy, looking classic to high precipitation supercell. You got your forward flank downdraft right here, your rear flank downdraft near Hazleton that caused a bunch of damage in that area, and a lot of dust plumes to be kicked up from this thing. You got your inflow right here. The sun represents where Anthony, Kansas is, and then this down here is the outflow boundary associated with that left split storm moving up from the south. As we progress forward here, this is at 7:23 p.m. We see the RFD move in more, and as well as the outflow boundary of the left split begin to encroach on the supercell and impact the rear flank downdraft. But the RFD is so strong, it kind of holds that part of the outflow boundary back, which I think is really fascinating. However, through here, it's able to move up. And you notice this little diamond shape here is where the Anthony EF2 rotation is. So you have a broad level of rotation here, which I think a lot of people are confusing for this. I do think that there were tornadoes here with this setup here, and that would have been a lot like we saw, for example, in Hawley, Texas last year, or in Oklahoma in the 2012 case that came out last year with that left split interaction. They're producing a tornado, a mesocyclonic tornado, near where the main mesocyclonic tornado processes would happen underneath the supercell. However, we have to look a little beyond that, because as we can see, the low-level rotation moving northwest here that would become the Anthony EF2 is nowhere near the supercell mesocyclone, so it can't be mesocyclonic. However, we notice that the inflow does start to back the closer we get to this supercell. And along this outflow boundary, you're going to have vorticity and all that kind of stuff that you would see along outflow boundaries. So we'll talk about that more here in a second as well. So more time goes by, left split continues to move north, and now we can see that rotation has gone up further here, and you'll see it better on velocity. That's now the ongoing EF2 tornado, still a few miles south of where it caused the EF2 damage, but that's moving rapidly to the northwest. So you can see the supercells also drawing further to the east, and this circulation, now the EF2, is much closer to the mesocyclone. And it is also interacting with this inflow that's being pinched off. It appears that it's being pinched off between the left split boundary as well as the forward flank downdraft boundary. And I think that also could have accelerated the inflow due to Bernoulli's principle factors kind of going on here. So we would have seen probably an acceleration of this inflow through here all the way from Anthony westward, as well as perhaps a pressure drop if that Bernoulli's principle is applied here. If that did occur here, this could have easily allowed for a pressure drop, which would have allowed for even more vorticity stretching and lift, and therefore vortex production along this outflow boundary. Whew, almost there. So, looking at this in velocity now, it'll make it a little bit easier to point out. So, we see Anthony here, the large inflow area into the supercell and the rear flank downdraft here. Now, going forward, you can see that left split outflow boundary here, and then the rotation a little bit better on velocity here. And then also what appears to be some of those those normal mesocyclonic funnels and tornadoes associated with the main supercell that would have occurred just to the east of Hazleton. Although they're not in the database, I do think that based on some chaser photos and videos that there were probably a couple tornadoes through here, at least one. However, this rotation, watch that rotation as that moves further to the north into the northwest. We see that become much more intense here, and we also see another rotation here to the west, likely a mesocyclonic tornado, but probably pretty brief if I had to guess, because that only lasts a couple scans. But then we see this here, and it's getting closer to the mesocyclone as well as the backed inflow, which is now being constricted and likely accelerated through here with a pressure drop thanks to those Bernoulli's principle factors that we discussed. So here is also something I wanted to note. So it's very similar to the last slide, is that you can see the mesocyclone here, your EF2 circulation here, although this one does show that new circulation that developed just to the southeast of it, appearing to be born from the same process, just a smaller version of the EF2. There was never a confirmed tornado here, but it is very possible that there was a brief tiny one, or one that just couldn't develop all the way. But notice along this outflow boundary, which is the left split's outflow boundary, we see these kinks along this outflow boundary. I think that's indicative of rotation and vortex production along this, as those kinks would indicate areas where there's a little bit more convergence happening there. So it's something that you would see like a lot in a squall line with mesovortex tornadoes and QLCSs, and this mesocyclone, the winds would back the more that you get, the inflow winds would back the closer you get to it, and therefore this would be comparable to how you see a cluster of tornadoes and tornado reports the closer you are to a surface low or the apex of a bow echo and QLCL type tornado outbreaks, because at that location you have a little bit more convergence and more wind backing, and therefore directional wind shear going on there as well. So here's one of the kinks that I saw that day, actually. It's actually this one here, just to the southeast of the Anthony, Kansas Town Center. So I was on the east side of Anthony, just east of Anthony, looking south, and saw this. I didn't notice at the time, but after going back, I figured out, okay, that's what this is here. So here's one of those kinks that you can see along that outflow boundary. You also got some scud here, implying that there's likely some lift going on. So that's pretty cool there, and indicates that this is a buoyant environment capable of producing vorticity, stretching vorticity, if any is produced here, which the closer you are to this mesocyclone, it appears that the more vorticity you have and are able to stretch. Going further east, here is another visual of some of those kinks from a different angle. This was taken about 5 to 10 minutes later. As you can see, tried to annotate the best I could here that this left split outflow boundary here is kinking, if you will, right through here, and also up here, and surging outward a little bit more here, and then also ingesting inflow notches through here. Now, technically this is happening at the ground, but I annotated it in the sky, as it's a little bit easier to see that way. And here is one more little graphic I put together, kind of showing how the backing of these inflow winds here really play such a significant role in why the Anthony tornado developed the way it did, and why the rest of the outflow boundary did not produce anything like that. As you can see, the closer you get along the left split outflow boundary to the mesocyclone, the more and more the winds start to back. And not only is it being constricted through here from between the outflow boundaries, but it's also converging more. So the closer you are to the mesocyclone, because of that wind backing, that you have more convergence here along that left split outflow boundary closer to the meso. So therefore, this would represent your EF2 tornado. This would represent the circulation just to its south and east. And this would represent the other kinks that were further east along the boundary that I was able to document. And you can see that they have much left of a wind shift than, say, way over here closer to the meso due to those backed winds. And once again, the sun represents the Anthony Town Center. Although the merger of the left split outflow boundary into this tornadic supercell greatly diminished its severity and tornado threat and prevented it from behaving more like the Valley View and Claremore tornadic supercells that Trey talks about, it evolved in an especially dangerous way, as what originally was not supposed to be a tornadic environment and was supposed to be an area that you'd be able to chase in near a supercell that would be safe and dry, became a heavy rain-wrapped and also intensely efficient area of vortex production underneath the storm, fostering significant tornadogenesis in locations that were not exactly anticipated to do so. This is extremely crucial for chasers, spotters, emergency service operators, and any others operating near severe storms, as this presents a new challenge in the field that could very easily be dangerous and unpredictable. Thanks for listening, and thanks, Trey. I appreciate it. Now back to you, buddy.
As you can see, the tornadogenesis process accompanying the Anthony supercell was unique and made for a highly dangerous situation for storm chasers in and around the storm's area of interest. Big thanks to Mikey for his insight into this storm. So hopefully that gave you some insight into the complexities of the environment across much of the moderate risk during the day. The left splits from the early Texas convection were no doubt a saving grace for what could have been a robust daytime severe weather event across central Oklahoma. However, the event was far from over. While all this was happening to the north, additional storms developed around 7 p.m. in the wake of the earlier storms in northwest Texas. They quickly became robust, taking on supercell characteristics and producing large hail. Additional updrafts initiated to the southwest of the complex, eventually interacting with its western flank. The trailing updrafts quickly organized, proceeding to conglomerate into a single supercell and develop a well-defined hook echo. An eventual EF3 tornado began at 9:39 p.m. just north of the town of Sunset, tearing a nearly 50-mile path through the northern suburbs of Dallas-Fort Worth. The tornado most notably impacted a truck stop along Interstate 35 in Valley View, inside of which over 100 people were taking shelter. After the Valley View tornado ended, the storm produced a couple other brief tornadoes before dissipating. Let's take a look at a series of RAP model soundings in proximity to the Valley View supercell to get a look at how the environment evolved into the evening. These were pulled from Gainesville, Texas, just over 10 miles from the tornado as it crossed Interstate 35. Starting at 12Z, we see a similar environment to that sampled by the morning observed sounding at Fort Worth. Ample instability was elevated atop a capping inversion and relatively shallow moist layer. The wind profile featured strong deep layer shear but extremely limited low-level shear thanks to the overall unfocused surface pattern. As we headed into the mid-afternoon time frame, instability blossomed to extreme levels with mixed layer CAPE exceeding 4,300 joules per kilogram. The atmosphere remained capped thanks to slightly cooler surface temperatures versus areas to the west where the initial supercells had developed, and the hodograph continued to exhibit little low-level curvature despite some veering of the low-level winds with height. This began to change by early evening. While instability had remained extreme, low-level shear had ramped up significantly by 0Z around the initiation time of the cluster out of which the Valley View supercell would blossom. The hodograph now possessed ample curvature in the low levels with over 300 meters squared per second squared effective storm relative helicity. All in all, this was a pretty textbook environment to support significant tornadic supercells, and it would only improve through the evening. By 3Z, the hodograph had become absolutely massive, associated with almost 1,000 meters squared per second squared effective storm relative helicity. Couple that with the persistent extreme instability, mixed layer CAPE had remained near 5,000 joules per kilogram, and you have a truly upper echelon environment for significant to violent long-track tornadoes, on par with or even exceeding events like April 27, 2011. So that begs the question, why didn't the Valley View supercell produce a top-tier violent tornado? Sure, it produced an EF3 that remained in progress for nearly 50 miles in 2 hours, but this proximity environment would suggest that this was well shy of its ceiling. First, we must confirm whether or not this proximity environment is even realistic. After all, Gainesville, from which this sounding was pulled, was situated in the forward flank of the supercell at this time, and there is at least some weak indication of convective contamination in the sounding. However, the subsequent sounding at 4Z shows a very similar environment with minimal convective contamination, so it appears that the incredible proximity environment was not induced by convection. Also, even though it's based on the same RAP model, the effective storm relative helicity map in the SPC Mesoanalysis archive shows a broad swath of 300 to 400 meters squared per second squared SRH, with multiple pockets of 500 to 600 plus meters squared per second squared, not just in North Texas. This may have been a product of heterogeneity in the strengthening mid-level winds. In other words, smaller scale pockets of stronger flow embedded within the broader mid-level wind field. Therefore, the Gainesville proximity sounding appears to be representative of the actual environment, even if perhaps slightly aggressive. While the environment was incredibly favorable for strong to violent long-track tornadoes, it wasn't perfect. There was a subtle warm nose between 850 and 700 millibars that had persisted through the day and into the evening, never fully eroding. This may have slightly impacted the robustness of low-level updrafts in this environment, although you would expect the overwhelming low-level shear, which can add to the overall buoyancy, to help overcome this. Still, it may have had an impact. In addition, vorticity in the lowest 200 meters or so was quite crosswise. As a refresher, streamwise vorticity exists when the storm relative wind vector, drawn from the storm motion to the level of interest on the hodograph, is parallel to the horizontal vorticity vector at that level, which is always perpendicular and to the left of the hodograph. When these two vectors are more perpendicular to one another, you have crosswise vorticity at that level. Low-level streamwise vorticity is much more favorable for tornado production in supercells, but tornadogenesis can still occur with significant low-level crosswise vorticity. Even though the streamwise component of the vorticity may be small, it adds up over time. But significant crosswise vorticity can make it much more difficult for tornadogenesis to occur and strongly tornadic activity to be maintained. In this case, notice how the near-surface layer featured ample crosswise vorticity. Therefore, even though this was an extremely upper echelon environment, it wasn't quite pristine, perhaps explaining why the Valley View supercell was unable to produce as formidable a tornado as it could have. Let's switch gears once again to Oklahoma. Although left splits had negatively impacted the environment across western and central portions of the state, the environment over eastern Oklahoma had remained untapped. Interestingly, around 7:30 p.m., a few storms developed in the immediate wake of the old batch of storms that had earlier produced the Mutual tornado. Unsurprisingly, they struggled as they moved through the overworked air mass until they approached the Interstate 35 corridor. Here, the environment started to become more and more favorable for storm intensification, with warmer temperatures and richer moisture with eastward extent. Just before 9 p.m., a new updraft initiated on the backside of the westernmost storm and rapidly became supercellular. After struggling with outflow dominance for a bit and undergoing a series of subtle mergers, the supercell intensified as it passed north of Tulsa, undergoing tornadogenesis at 10:19 p.m. northeast of Owasso. This tornado would tear through the town of Claremore, producing multiple instances of EF3 damage along its 24-mile, 40-minute track. Immediately before the tornado begins, notice the small shower that merges directly into the supercell's hook echo. It appears that this merger may have aided in tornadogenesis, perhaps by inducing a rear flank downdraft surge. As the merger occurs, the hook slingshots forward and begins wrapping up. Inbound velocities within the rear flank downdraft drastically increase, and tornadogenesis occurs. This is very similar to what happened with the Moore, Oklahoma tornadic supercell on May 20, 2013. In that case, a small shower also merged into the developing hook echo of the Moore supercell. As that happened, the hook echo began wrapping up, inbound velocities increased, and tornadogenesis was consummated. We discussed all of this in my meteorological breakdown on the Moore EF5. I'll put a link to it in the description box below. The Claremore tornado exhibited a well-defined debris ball in reflectivity before dissipating near the town of Pryor. The storm produced a few more brief, weak tornadoes as it tracked east. As it approached the Arkansas border, another small shower merged into the supercell's hook echo. Shortly after this occurred, the storm once again underwent significant tornadogenesis. The tornado quickly expanded into the largest tornado in Arkansas state history, with a maximum width of approximately 1.8 miles across. It produced EF3 damage near Decatur, Arkansas, alongside an anticyclonic satellite tornado that produced EF2 damage on the south side of town. The storm continued to produce strong tornadoes for several hours as it moved east across the Ozarks Mountains in northern Arkansas, finally meeting its demise as it was absorbed into the trailing convective complex just before 6 a.m. on the 26th. Let's take a look at a series of RAP model soundings from Fayetteville, Arkansas to see what the environment looked like near this storm. Throughout the day, the atmosphere destabilized efficiently with strong instability in place by early afternoon. Like areas to the south, hodographs remained very straight until early evening thanks to the strengthening low-level jet. Eastern Oklahoma and western Arkansas were somewhat removed from the axis of the low-level jet, but there was still enough low-level shear to support significant tornadoes, especially with strong instability. Before we continue, I'd like to point out this unusual low and mid-level drying trend that truncated the low-level moist layer and introduced a strong cap back into the environment. Switching over to the 850 millibar map on SPC mesoanalysis, we can see that this low-level drying trend emanates from the Red River area at 23Z and spreads into eastern Oklahoma with time. I'm unsure if this is legitimate and, if so, what would cause it, or if it's just a RAP model quirk. I tend to believe the latter, as the amount of dry air and associated capping, as well as the shallowness of the moist layer exhibited in these RAP soundings, would be quite detrimental to significant tornadic activity, especially with less low-level shear than areas to the west and southwest to make up for it. With this caveat in mind, the environment was favorable for intense tornadoes, with moderate to strong instability and veering and strengthening winds with height. This led to adequately curved low-level photographs and 0 to 1 kilometer storm relative helicity near 300 meters squared per second squared. Alright, let's shift gears into the following day, May 26th. In the same outlook that initiated a risk area for May 25th, the SPC also outlined a 15% contour for May 26th, centered over the Ohio and mid-Mississippi River valleys. This was upgraded to an enhanced risk equivalent 30% contour in the subsequent Day 5 outlook on May 22nd. The enhanced risk remained in subsequent outlooks, and by the midday Day 2 outlook on May 25th, the SPC had outlined a 10% hatched tornado risk area encompassing southeast Missouri, southern Illinois, western Kentucky, and northwest Tennessee. This was outlined to cover the risk for strongly tornadic supercells along and north of the outflow boundary from a complex originating from the convection on May 25th. Confidence in this occurring remained somewhat low until the 20Z Day 1 outlook on May 26th, which featured an upgrade to a level 4 out of 5 moderate risk with an associated 15% hatched area for significant tornadoes. The main meteorological question with the setup on the 26th was the degree of atmospheric recovery behind the morning complex. Those questions were quickly squashed as ample clearing began in earnest immediately after the complex's passage. The outflow boundary in question was initially situated from the Missouri boot heel into northern Arkansas and northern Oklahoma, before becoming much more diffuse with time thanks to strong surface heating on both sides of the boundary. These diffuse outflow boundaries are optimal for tornadic supercells to anchor to, as the minimal temperature gradient across the boundary allows for limited boundary motion, and the air mass to the north can also favor tornadic supercells given more backed surface winds, stronger low-level shear, and stronger surface vorticity. Another feature of interest was a prefrontal trough or confluence band that tracked across the region. By early afternoon, the cold front was situated across central Missouri into eastern Kansas, Oklahoma, and north Texas, as evidenced by the shift from northwesterly to southwesterly winds and temperature gradient across the boundary. Farther east in the warm sector, notice the confluence band that was in place, with southwesterly winds immediately ahead of the cold front and more southerly to southeasterly flow across much of southern Missouri and Arkansas. This was expected to be an initiation mechanism for storms across this region, as was the cold front. Up at 500 millibars, our main trough from the previous day was situated from Kansas to Texas at 12Z and had undergone slight amplification and taken on a negative tilt. A lead shortwave and jet streak were positioned over Missouri and Arkansas, aiding in the persistence of the convective complex left over from the 25th. By mid-afternoon, the trough had meandered east with the exit region entering Missouri and Arkansas, providing adequate large-scale forcing for ascent timed perfectly with maximum daytime heating. Similar to the previous day, only subtle defluence was present at 300 millibars heading into the afternoon. Deep layer shear vectors were quite perpendicular to the confluence band but more parallel to the cold front, indicating that storms would likely congeal into an MCS fairly quickly along the cold front, with more discrete supercell development to its south, near the confluence band and elsewhere in the open warm sector. The broad low-level cyclone would continue to meander off to the northeast, which allowed the low-level jet to veer and weaken slightly across our area of interest. Still, low-level shear would remain elevated, especially in areas with more backed surface flow, thanks to significant veering of the winds with height. Taking a look at the morning observed sounding at Little Rock, Arkansas, we see an environment that's quite favorable for severe weather. Steep lapse rates aloft had advected into the region to provide for some robust capping, but ample instability was elevated above this inversion, expected to increase substantially by afternoon, with strong surface heating and continued warm advection behind the morning complex. The wind profile was impressive, with significant low-level hodograph curvature and nearly 500 meters squared per second squared of 0 to 1 kilometer storm relative helicity amid strong deep layer shear. By early afternoon, the cap had remained somewhat stubborn, but with the approach of the shortwave and convergence along the aforementioned boundaries, it wasn't going to take much to initiate storms in this environment. The low-level moist layer was moderately deep, extending up to just below 850 millibars, and instability had continued to increase. Although low-level shear had decreased some, notable veering and strengthening of the low-level winds with height maintained clockwise curved hodographs and effective storm relative helicity in excess of 200 meters squared per second squared. Couple this with a vorticity-rich environment along and north of the diffuse outflow boundary, and the environment was certainly favorable for tornadoes with a bit of further cap erosion. Storms initiated just after 1 p.m. across eastern Kansas, Missouri, and northeast Oklahoma, along the aforementioned boundaries. Given the robust environment, storms rapidly became severe. As expected, storms along the cold front congealed into an MCS fairly quickly, while discrete supercells persisted to its south in the open warm sector. These eventually became tornadic, as did additional supercells that developed well to the east across southern Illinois and western Kentucky. Several of these tornadoes were strong to intense, including an EF3 near Mountain View, Missouri, and an EF2 near Eddyville, Kentucky. With time, the frontal MCS overtook the remaining discrete supercells, continuing to produce significant damaging winds and embedded tornadoes. Let's analyze a series of RAP model soundings at Cape Girardeau, Missouri, a good centroid for the significant tornadic activity that occurred on the 26th. As the morning progressed, you can see the impacts of the early convective complex on the environment. However, by early afternoon, recovery had begun in earnest as surface temperatures warmed and dew points increased. Mixed layer Cape had breached the 4,000 joules per kilogram mark, including impressive low-level instability. Take a look at the fat Cape profile in the lowest few kilometers of the atmosphere. 0 to 3 kilometer Cape was approaching 250 joules per kilogram. Given fairly average low-level and deep layer shear for tornadic supercells, the extreme low-level instability was key in stretching surface vorticity into the vertical to aid in tornadogenesis. So that's going to wrap things up for this video. The May 25th and 26th event was just one in a series of robust tornado outbreaks that contributed to 2024's historic tornado count, and like many of its 2024 counterparts, featured several individual storms that exhibited unique behaviors and characteristics. Thanks for watching, and we'll see you in the next video.